Hello everyone, and thank you for joining us today. My name is Wyatt Pena, and I am the Director of Operations at Ridgetop Group in Tucson, Arizona. For today's Aircraft Health Management Workshop, I'll be joined by Mr. Sheikh Ahmed with Kingsley Instrumentation, and we are excited to be able to participate in this program session to present our slides on diagnostic and prognostic efforts for integrated vehicle health management in aircraft systems. For today's agenda, we will start out with a company overview, an abstract on the entire workshop, some background information with IVHM methodologies and PHM frameworks, and we will then cover 5 different case studies that Ridgetop has worked on over the years. These case studies include helicopter gearbox systems, structural health monitoring for composite helicopter blades, aircraft power supply systems, intermittent connectivity in items such as cables, wire harnesses, and solder joints, and our final case study will be on electromechanical actuators, or EMAs, that are used in several different types of aircraft systems. We will then cover our ongoing case studies in other related fields, and then we will wrap up with a brief summary and then have a few minutes for questions and answers. So a little bit about Ridgetop Group. We are located in Tucson, Arizona, and we are a technology leader in reliability engineering, quality assurance, condition-based maintenance, prognostic health management, and integrated vehicle health management. Along with offering advanced diagnostics and prognostic solutions, we are also an AS9100D and ISO 9001:2015 certified facility that has been servicing the aerospace, automotive, industrial, and government market segments since the year 2000. Over the years, we have worked on several different government and commercial contracts to design, develop, and deploy some of the most innovative prognostic solutions for a diverse set of unique applications. So for the general abstract of today's workshop, it is worth noting that CBM, PHM, and IVHM are all application areas that Ridgetop has been focusing on for nearly 2 decades. During this presentation, we will cover a handful of different case studies that are related to physics of failure analysis, advanced diagnostics, predictive analytics, and how modular PHM frameworks can be used to develop a customized prognostic solution. I was fortunate enough to be able to participate in many of these case studies early on in my career, and the resulting technologies have allowed us to develop a unique set of hardware, firmware, and software-based solutions for other types of applications and customers. As we will cover in some of today's case studies, Ridgetop's products, solutions, and engineering services are aimed at increasing safety, efficiency, and operational performance, while also reducing maintenance and sustainment costs, which also happens to be some of the direct benefits from CBM, PHM, and IVHM practices. With these next few slides, we will provide a little bit of background information on IVHM methodologies and PHM frameworks. As I am sure many of you are aware, the way we conduct maintenance on our machines, vehicles, and aircraft systems has been evolving for quite some time. For many applications, maintenance practices and strategies can be grouped into these 4 categories of reactive maintenance, preventative maintenance, condition-based maintenance, or predictive maintenance. I have often seen CBM, PHM, IVHM, and predictive maintenance grouped together, but as we will cover in some of our slides, they have subtle differences. An example of this is actually shown here as prognostics and predictive maintenance, which is used in PHM and IVHM solutions, actually evolved from CBM practices. This occurred as engineers started to analyze trends and faults in historic data sets from CBM-enabled systems and platforms. I'm sure the way we view and carry out some of our maintenance routines will continue to evolve, and there is some exciting work being done in this space with new technologies like AI and machine learning. This particular slide shows the traditional bathtub reliability curve that I'm sure many of us are familiar with. Prognostic-based solutions are meant to capture data streams that exhibit a fault to failure progression signature on the latter half of this bathtub curve. As we know, the failure rate of nearly all systems and equipment tends to increase as they start to wear out. This bathtub curve offers a great conceptual view for a single system or component, but it doesn't necessarily capture the relationship of distributed failure rates of condition-based events that occur in systems of systems. We recently published a paper on that topic for the IEEE International PHM Conference in Detroit, Michigan, but it is outside of the scope of today's IVHM workshop. This next slide provides a good conceptual view of IVHM and PHM ecosystems, where you have 5 main operations to sense, acquire, and analyze a system or subsystem for one or more different failure modes. Based on your analytics and prognostic estimates such as remaining useful life and state of health, you can then act on and advise what types of actions should be taken or automated. As you might expect, all of these operations can be application dependent, failure mode dependent, and different faults can have different levels of criticality. Just because a lighting system may have failed in a helicopter, that doesn't necessarily mean your PHM or IVHM action should be to warn the pilot that urgent maintenance is needed in order for them to complete their mission. This next slide offers another view of a PHM system, except this time it's in terms of frameworks. In this slide, there are 5 different frameworks that need to be accounted for. The frameworks include a sensor framework to acquire your data, a feature vector framework to extract data related to a fault, a prediction framework to determine your RUL and state of health, and finally, you need a control and data flow framework that also interfaces with a fault management system and a performance validation framework. Each of these frameworks can comprise of hardware, firmware, and software elements, and over the years, Ridgetop has tried to modularize several of these technologies to fit within a certain framework or group of frameworks. So I know this slide can be a little tricky to follow with all the different arrows and notes, but thankfully the IEEE Reliability Society recently published a standard for these types of solutions. That standard is the IEEE 1856-2017 standard framework for prognostics and health management of electronic systems. And within that standard, there is a PHM functional model that is shown on this slide. As you'll notice here, this PHM model does a great job of identifying the 5 core PHM operational processes for sensing, acquiring, analyzing, advising, and acting. And then each of these are then further distilled into 8 functional blocks that are shown here. This model was also shown at the IEEE PHM conference that I recently attended to last month in Detroit. I also learned that some of the Ridgetop team members, such as distinguished engineer Mr. James Hoffmeister, was actually a part of the early working groups that helped develop the standard, and we look forward to staying active in the IEEE Reliability Society for future programs and work. Next, we'll move on to some of our highlighted case studies. Our first case study is related to a multi-year SBIR program we did while working with NASA. As a part of this program, Ridgetop was able to design and develop a wireless accelerometer that was embedded in the transmission gearbox of a 500 horsepower Bell OH-58 Kiowa helicopter. While conducting several different tests and designs of experiments at the NASA Glenn Research Center, Ridgetop was able to compare the efficacy of an embedded sensor versus traditional case-mounted accelerometers when detecting a cracked gear tooth fault. As shown in this slide, Ridgetop was able to detect a clear fault to failure progression signature by looking at the time synchronous averaging signal from the wireless sensor, which we now call RotoSense. This body of work served as the foundation for our Sentinel Motion product line, which was later adapted for monitoring bearings, wheels, and track components, as well as other industrial IoT applications. This next slide shows some key results highlighted by the NASA research here, and the cracked gear tooth fault that we were studying. There were also some good links for the full white paper and the NASA spin-off article, but some interesting observations that are worth noting is how we use our Adaptive Remaining Useful Life Estimator, or ARUL software, to normalize the TSA data and calculate the state of health and remaining useful life associated with that cracked gear tooth. By looking at the SOH plot, you can see where the experiment was stopped 2 different times to increase the crack in the gear tooth by filing that gear tooth down. After each stop, you can see where the state of health goes back up and then rapidly decreases until it eventually failed and the experiment was stopped. Each time the experiment was resumed, you can see the rate at which the state of health degrades is faster. Additional details are highlighted in our A-Roll software user guide for this particular case study, but it is worth noting that this next slide provides a visual of how Ridgetop has successfully modularized some of our technologies to meet the goals of PHM Frameworks and the IEEE 1856-2017 standard. For this case study, we have our sensing and data acquisition process being done with the Sentinel Motion Development Kit, or SMDK, and then we got the TSA analysis being done as the feature extraction, and then we got the predictive analytics being done with our A-Roll software to determine the state of health and remaining useful life. The next core PHM operational processes, according to the IEEE PHM standard, would be to implement the advise and act processes for this particular failure mode. This is something we are actively still working towards with industry partners for their own unique gearbox systems and platforms. Our second case study is also related to helicopters, except this time we worked with Boeing and a company in the Netherlands called Technobis to design, develop, and test a structural health monitoring solution, or a SHM solution, for the composite rotor blades on the Apache AH-64 helicopter. This case study used fiber brag grading sensors to detect strain, stress, bending moments, and temperature data streams with a fiber optic interrogator and an IoT gateway system. Ridgetop's role in this project was to lead the implementation of the IoT connectivity from the interrogator to the gateway system, which then hosted the data acquisition software and analysis toolbox. The system was flight tested in late 2017 and is another area that Ridgetop and Technobis continue to collaborate in. This next slide provides a visual of how the fiber brag grading sensors were embedded in the composite rotor blades and the block diagram of the interrogator that communicated with the gateway. The third highlighted case study we will discuss today is also related to work that Ridgetop has done with Boeing and the Apache helicopter. This program took place several years prior to the structural health monitoring project, and it made good use of Ridgetop's ring down technology that was based on a patented approach to monitor the loss of filtering capacitance and other failure modes in onboard power supply systems. Shown to the right, you can see where Ridgetop was able to capture the ring down frequency of healthy power supply and a degraded power supply. This case study for power supply prognostics was also extended to other types of power supply systems for both critical and non-critical applications. In doing this exercise, Ridgetop was able to develop the Sentinel Power product line as a toolbox for studying and analyzing 5 different types of failure modes. These include loss of filtering capacitance, loss of gain in the feedback loops, loss of phase margin, loss of filtering inductance, and loss of effective parallel resistance. Referring back to the IEEE 1856-2017 standard, Ridgetop's approach to these failure modes was consistent with the sense, acquire, and analyze operational processes that were covered on slide 10. For this particular example, we know that by analyzing the change in ring down frequency, you can generate a clear fault to failure progression signature shown in the lower right corner here. Our next case study is for intermittent connectivity in cables, wire harnesses, and solder joints. This case study was carried out with the U.S. Navy as they had a recurring failure mode with their high data rate cables used in retracting antenna mast systems on submarines. The issue for the Navy was that the cables were becoming kinked and bent to a point where they began to short or break open. In order to monitor for this failure mode, Ridgetop developed a smart sweeping probe to measure changes in impedance level when a high frequency RF signal was transmitted. The approach was similar to time domain reflectometry, and by doing this, Ridgetop was able to detect a clear difference between a healthy cable and a damaged cable, as shown in the lower right corner of this slide. Now, I know this case study isn't for an aircraft system, but the technology itself can be directly adapted for cables and interconnects used in aircraft systems. An example of this will be covered here on this slide. So it's also worth noting that this case study made use of Ridgetop Sentinel Interconnect product line, and the underlying SJBIS methodologies. Shown in the upper right corner is a cable power test avionics troubleshooting system that was developed for the FA-18 aircraft used by NavAir. That particular unit was able to test for opens, shorts, and power measurements in a matter of minutes, where it used to take hours to test with a multimeter or other types of test equipment. Going on to our final case study for today's workshop, we will revisit another multi-year NASA contract that Ridgetop did as a part of the model-based avionic prognostic reasoner program. This body of work resulted in a prognostic solution for 4 different failure modes, as circled in red in the block diagram on this slide. The first failure mode was for ripple voltage fault within a switch mode power supply. The second failure mode was for the switching transistor. The third failure mode was for the motor stator winding, and the fourth failure mode was for the rotating shaft. There are some related links on this slide that will go into more detail for this program, but I wanted to go ahead and jump to the next slide to show the fault to failure progression data signatures that we were able to capture for these different EMAs. As you can see here, there are 4 clear fault to failure progression signatures, and each of them can be analyzed with a rule to determine the state of health remaining useful life of the EMA. It is also worth pointing out that these failure modes were reproduced on EMAs that serve different applications, including aircraft systems. That EMA case study wraps up our highlighted topics for today's IVHM workshop, but there are a few other case studies that Ridgetop has been focusing on in recent years. One of them is the use of the IoT RotoSense units in the railroad industry, and the other is a battery health modeling, simulation, and analysis software called CellSage. Both of these focus areas have related tracks for PHM and IVHM implementations, and we look forward to presenting on those topics at future conferences. As a brief recap of today's workshop, we discussed some background information on IVHM methodologies and PHM frameworks. We also briefly covered the relatively new IEEE 1856-2017 standard and the 5 core PHM operational processes for sensing, acquiring, analyzing, advising, and acting on your prognostic data. We also covered 5 different case studies that Ridgetop has worked on, and we would be happy to start any new collaboration projects that related to these areas. With that in mind, I believe we have reached the end of our presentation, and we would like to thank you for your time, and we welcome any questions or comments that you may have. Thank you.